Hello, this is a video presentation for Group 20. We created a C++ programming group to calculate buckling. Here is the list of our group member, with Aizad being our group leader. This is our content of our video presentation. We have introduction, methodology, result and calculation, discussion, and lastly conclusion. Mechanics of materials, also known as strength of materials, is a branch of engineering mechanics that investigates the behavior of solid materials under various external forces. This field is a fundamental to design and analysis of structure. Buckling is a critical issue in structural engineering and mechanics, occurring when slender structural members such as columns or beams succumb to compressive loads. Buckling is fundamentally a question of stability for slender structures subject to compression. There are a couple of types of beams that can be considered undergo buckling. Our program involves the calculation of what it needs to calculate buckling in a specific beam. Now we move on to methodology. At the start of the program, the user have to input the number of beams and move on to while loop where user has to input a negative number of beams. If true, user will be asked to input a positive number. If false, compiler will move to for loop. For for loop, the compiler will display types of support of beam, and then it will move to while loop. User has to input a negative number between 1 to 4. If true, user will be asked to input positive number of 1 to 4 to display the types of support of beams. Next, it will move to while loop, where user will be asked to input negative number of elastic modulus. If true, compiler will ask to input positive number of elastic modulus. If false, compiler will display none. Then it moves to while loop. User will be asked to input positive number of value of length. Now we come to the end of our program, where the compiler will calculate the value of the moment of inertia of the specific beam chosen by the user. Then the compiler will calculate the value of critical buckling load for each pin and display the result. With that, it comes to the end of our program.
We use the formula to calculate buckling theoretically, which is critical loads equals to pi squared times EI over square of KL, while I, which is moment of inertia of beam, can be calculated by 1 over 12 BDQ. These are dimensions used in the program and calculation, and value of moment of inertia, which is calculated theoretically by using this dimension. It becomes 7.2 to the power of negative 7. Value of constant K are different for each type of pin support. Value of K for pin ended is 1, for pin fixed ended is 0.7, for fixed ended 0.5, lastly free fixed ended 2.0.
So after we run the program, we got our desired output. So for the first, enter the number of beams to be calculated is 1. Enter the type of support from beam 1. So now we choose number 1 is pin ended beam. So for the elastic modulus, we choose 200 gigapascal. For the length of the beam is 2 meter. Width of the beam is 0.04 meter. And for the height is 0.06 meter. And the program calculate the moment of inertia of the beam, which is found to be 7.2 times 10 power of negative 7 meter per watt 4. And as a result, for the critical buckling load that has been calculated by the program, is found to be 355306 Newton. So we compare the result with the theoretical formula result. So the value of critical load of the formula is 355305.7584 Newton, and we compare it by find the percentage error. So the percentage error is 6.8 times 10 power of negative 5%. So next is, now we choose pin fixed ended beam. So same like before, we use the same elastic modulus, length, width and height of the beam. So the moment of inertia of the beam that has been calculated is 7.2 times 10 power of negative 7 meter per watt 4. And as a result, for the critical buckling load of the beam, our PCR is 725114. Then we compare the program result with the theoretical formula. So it's going to be 725,113.7927 Newton, and we compare it. We use percentage error to compare. So we found that the percentage error is 2.86 times 10 power of negative 5%. So next is fixed ended. So same like before, all the elastic modulus, length and width and height is same as like pin fixed ended beam. So and the moment of inertia of beam is also same, which is 7.2 times 10 power of negative 7. So and for the critical bucking load of PCR, it's going to be 1.42122 times 10 power of 6 Newton. So we compare the result with the theoretical formula. So the value of critical load is PCR is equal to 1421223.034 Newton. So the percentage error is found to be between the program result and the theoretical formula is 2.13 times 10 power of negative 6%. So lastly is free fixed ended beam. So similar to before, now we choose number 4 is free fixed ended beam. So the elastic modulus, length of the beam, width and height, and also the moment of inertia of beam is same like before, which the moment of inertia of beam is 7.2 times 10 power of negative 7 meter power of 4. While for the critical bucking load that has been calculated by the program is 888 to 6.4 Newton. Then we compare with the theoretical formula. So the value of critical load from the theoretical formula is 888 to 6.43961 Newton. Therefore, the percentage error is found to be 4.4610 times 10 power of negative 7%.
So the first discussion that I would like to point out is the answer is correct with manual calculation. But the problem is there is rounding errors where because the real numbers in the computer is represented by finite precision, and there could be different in value of constants like pi, where it is infinite in computer. The second is the usage of the IOMINE IP header and the function that comes from IOMINE IP, which is set precision. These two is essential in calculating critical load, because with IOMINE IP it makes us it enables us to display the results precisely, and the function of set precision is to show exactly how much digit we would like to show. In this case, we show up to 8 digit after decimal point. The third discussion that I would like to point out is in our code, we assume that the user would like to use the shape of a rectangular cross-sectional area. So I think one of the improvement that we could make in the future is to make an option where the user can choose which shape that they would like to calculate. And lastly, I would like to point out that this is really beneficial to the engineers, because it is a tool that will help engineer to save time and effort in order to calculate buckling. It is also will help the production design engineers to be more productive in their design and become more efficient in their work.
Hello, I will present the conclusion. The first point is output precision. The program helps us to avoid precision challenges such as rounding errors. We also get to see the variation between the decimal points between the theoretical results and the results we calculated manually, and the results it is calculated by the program. And the second is the importance of the formula. It is important to use the right formula to calculate the buckling, since different shapes require different formula of buckling. And thirdly, the utility. The program helps us save a lot of time and enhance accuracy, since we just need to input the measurements and it will display the buckling, and we don't need to calculate it individually. In conclusion, program is a valuable asset in structural engineering, showcasing synergy between theory and computation. It also helps in design and analysis for a beam when we're creating a beam. That's all. Thank you from us.